Hi there, everyone. Welcome back. We continue on with our discussion of dynamics, and today is a very special day. We're going to talk about tension. So tension, just in a general sense, is a force that occurs whenever an object is being pulled. So up until now, some of the forces that we've seen as tension forces, we might have just called them an applied force. So you can imagine that if we've got some system, maybe we've got two objects attached by a rope. When you pull on the first object, the rope pulls the second one along. So what we'd say in this case is tension is an internal force. It's sort of happening inside the system. And so we're going to define tension as being an internal force that acts at all points. It acts at all points along a rope or a string or a chain or whatever it is in both directions. So we'll see a few examples. Basically, I'm just going to work through a bunch of worked examples where we might try to figure out how much tension is being exerted along a rope, that sort of thing. So first example, imagine we've got two carts attached by a rope. So we're applying a force here to this cart to the right, and that's going to make these carts roll along to the right. It also tells us that there's no friction in this system, so the wheels are really good and it's just going to kind of glide along. But there are other forces that are happening here. Like some really obvious ones, for example, are force of gravity. So in each case, there'd be a force of gravity, maybe we'll call this Fg1 and Fg2 pulling down, and then these carts are not falling through the ground because they're supported by a normal force, so maybe Fn1 and Fn2. And it's really important when we set up these problems that we draw all the forces on the system. Some of them are obviously going to be important, like the applied force. Some of them might not be as obvious, but they might end up being really important. So it's important that we draw them all out. And then so of course there's a tension force because that's what this whole lesson's about. Just imagine this, so when I grab on that first cart and I pull it along to the right, then the rope itself is going to be pulled taut. And that's because there's a tension in that rope that's pulling the cart along for the ride. So it is when we talk about tension, we say that the tension, it acts at any point in the rope. Like the tension is everywhere in that rope. If I cut the rope at any point, then the second cart stops accelerating. So I can draw this tension wherever I want. I'm going to draw it in one case right here. This force of tension, I call it Ft, is pulling this cart to the right. But the thing to recognize, if you think back to Newton's third law, is that the tension that pulls the second cart along to the right, it has an equal and opposite force on the other end of the rope that pulls this cart backwards. So these two tension forces are exactly the same, and they oppose each other, right? But that doesn't necessarily mean that the system can't accelerate, as we'll see in a second. So first thing we're looking for is what is the acceleration of the system, okay? So we're going to come up with a net force equation, so F net equals, now when I look at all of the forces in my system, I'm going to say to the right is my winning direction or is the positive direction. So I've got an applied force to the right, and then if I look at it, one of the tension forces is also to the right. So I'm going to add my tension force, okay? And then that's all the forces to the right. And now I've got my forces to the left. Well, I've got a tension force to the left, so I need to subtract my tension force there. And that is going to equal MA. There's two things I want you to notice here. First of all, when I look at the whole system, so in this first treatment here, I'm looking at the entire system, all of the things. When I look at the whole system, the tension force is going to cancel out. And this is always going to happen because the tension force is this internal force that's internal to the system, and it's always equal and opposite to itself. So those forces cancel out. But the other thing I want you to notice is, what mass am I talking about there? Well, since I'm talking about, I looked at the whole system, I considered all the forces on the whole system, then in this space right here, I have to use the total. I'm going to put a little T there for total mass because I have to use the total mass of the system. So just rewriting this here, I've got my applied force is going to equal the total mass times the acceleration. Well, now I can just go ahead and solve. So the acceleration of the system is going to equal the applied force divided by the total mass, which is 40 newtons. 40 newtons divided by, looks like 4 plus 6 is 10. So it works out to be about 4.0 meters per second squared. And that's positive or to the right or whatever you like. So The note there is that whenever you look at the whole system, the tension force cancels out. Tension cancels out of the whole system F net. So when I create my net force equation and I look at the whole system, the tension force is going to cancel out. Now, think of this another way. I could have just treated these two carts that are connected by rope, I could have just treated this as one big 10 kilogram cart, and the acceleration would be the same, right? And that's the same idea. So then the second question says, okay, so now find the tension in the strings connecting them. Okay, well, I obviously can't look at the whole system because if I do, the tension force is going to cancel out. So now, in this case, I'm going to do a different trick. I'm going to look at just one half of the system or the other. I'm going to split this problem up into two possible chunks. Now, I'm going to do a little extra work here. You don't have to do all of this, but just to kind of prove a point the first time around, I'm going to do it this way. Because the tension force is the same, whether we're talking about the tension force that's pulling M2 along or the tension force that's pulling back on M1, those forces are the same. I should be able to look at either of the two masses and get the same answer. So let's just try that out. So let's just look at M2, for example. If I just look at M2, and sometimes it's helpful, just put your hand right over the picture of M1. It's not there, it doesn't exist. What is the F net equation for mass 2? Well, the F net equation for mass 2 would be the tension force to the right, and that's it, no losers, is equal to the mass times the acceleration. Something important to recognize though, which mass should I use in this case? Well, if I'm only looking at M2, then I should only use mass 2. But note that the acceleration of both of the blocks or the carts has to be the same. Otherwise, like the rope would be stretching out or something funky would be happening. So to find the tension, that's just mass 2 times the acceleration. So mass 2 is 6, the acceleration is 4, and what do you know, I get 24 newtons. Okay, so again, just to prove a point, I should be able to do this same idea, but just look at mass 1, and I should end up with the same answer. So if I I use my hand to cover up mass number 2, and then I look at mass 1, then my net force equation would be a little bit different. The winner here is the applied force, and the loser is the tension. And that's going to equal MA, but since I'm only looking at mass 1, then this is mass 1. So doing some algebra, I can see that FT, my tension force, is going to equal the applied force minus M1A. Okay, it's a little more work here, but I've got 40 minus 4 times 4, which is 16. 40 minus 16 is 24 newtons. Okay, so you don't have to solve every problem twice, but just the point here to notice that it shouldn't matter which part of the system you look at. In any given problem, probably one of the masses or the other is a little bit easier for you to think about. So by all means, just think about whichever is easier for you if you're looking for the tension. Okay, so the note here says, since it cancels out of the total F net equation, we will only consider the forces acting on one object. Okay, and since tension acts equally on both parts, we can use either one. It doesn't matter. So pick whichever one's easier for you. Okay, but the general strategy is pretty straightforward. If you don't know the acceleration, look at the whole system. If you don't know the tension, look at one part or the other, and it's just F net equations all the way. What I do want to point out though is that students sometimes get caught up on the idea, they just say, hey, but what's the formula for tension? And the answer is, I don't know. That completely depends on the situation. There isn't one particular formula for tension like there is for maybe gravity or friction. It's going to really depend on what's going on. So let's look at another example here. So we've got two equal masses hanging from a pulley, okay? So these two masses hanging from a pulley, I've got mass 1 would have a force of gravity pulling down this way, the FG1, and mass 2 would have a force of gravity pulling down this way, FG2. Now, those masses aren't falling down because on both of them upwards would be tension forces. Now, in this case, this is in equilibrium. The forces aren't accelerating because the two weights are the same. But the point I'm getting at here is when you have a pulley problem, it's not immediately obvious which forces are working with which forces. Like, for example, I can see that both forces of gravity are both down. But even though those forces are both down, since they're connected by a pulley, they're actually kind of fighting against each other. You could imagine if one mass was heavier than the other, it would start to accelerate down, the other would accelerate up. So sometimes in order to picture these problems, what we do is we take the two hanging masses and we take the pulley and we imagine that we just like unfold the whole problem and we put it all in a line. So in this case, if I move the forces along with it, my force of gravity 1 is kind of going this way. And my force of gravity 2 is going this way. And we can see then that our tension forces, tension force, well, 1, but they're the same, is this way, and then the other tension force is that way. So when I put them kind of in a line like this, I can see which forces are fighting which other forces. FG2 really is fighting FG1, and whichever is larger is going to win. So let's do a practice problem. Here I've got two unequal masses. So again, I'm gonna draw this picture here. I've got FG1 pulling down there, and then FG2, which is smaller. And then I've got tension force 1 upwards, and tension force also the same tension force, also upwards. And a reminder that these two forces are the same. The tension forces have to be the same. Even when the weights are not equal, the tension forces have to be the same because the rope's not stretching. If I want to visualize this all in a line like I did before, and if this helps, do it, and if it doesn't help, then you don't have to. But I've got FG1 this way, and then a smaller FG2 that way. And then I've got my two tension forces kind of pulling inwards on each of these masses, FT and FT. Okay. So I want to find the acceleration of the system. So again, since I want to find the acceleration of the system, I'm going to think about all of the forces on the system. So I'm going to do an F net equation, and that's going to equal, well, the FG1 is larger, so it's winning. So now I'm going to choose the left as the winning direction. So that means I've got FG1 is winning. Notice that I've also got one of my tension forces pulling to the left, so I'm going to add my tension force. And then pulling back to the right is one of my other tension forces and FG2. Now, at this point, you're probably already saying, like, do we have to do this? And the answer is no. You do not need to every single time write out plus tension minus tension. I'm just trying to prove a point, and we'll skip that in future steps. So I've got FG1 minus FG2 equals MA, but since I'm looking at the whole system, all of the masses, then this is the total mass. So solving for the acceleration is going to equal Fg1 minus Fg2 divided by the total mass, which is m1g minus m2g divided by m1 plus m2. And I guess you could collect like terms there if you wanted to, if you want to be fancy. Let's see here. We've got 6 times 9.8 minus 4 times 9.8 all divided by 6 plus 4. At least I chose some easy numbers to work with. Now cranking this all through your calculator, you end up with an answer of like right around 1.96 meters per second squared for our acceleration. Okay. And now we've got to find the tension in the string. So it doesn't matter which mass we choose. We can choose mass 1 or mass 2 to find the tension. Personally, I might look at mass 2 just because tension's the winner over there. So maybe that's a little bit easier, but I mean, it doesn't really matter. You should get the same answer either way. The net force equation, when I look at mass 2, is going to be tension minus Fg2 equals MA. And a reminder, since I'm only looking at mass 2, this is only mass 2. And so tension is going to equal Fg2 plus M2A, which ends up being right around 47 newtons. And again, if you did the same calculation looking with mass 1, you should get the same answer. Okay? So again, when solving for acceleration of the whole system, if you want to find the total acceleration, we consider both masses. And when finding t, we can use only one mass. Okay. All right. We're going to do one last example here, I think. This video is getting a bit long. So Now I've got a mass hanging on a table. Hanging on a table? I've got a mass sitting on a table, and then attached to a pulley hanging off the end, I've got another mass. So let's draw all the forces, okay? So I'm going to call this M1 here. So here's my little M1. Here's my M2. I don't know why. The hanging mass always gets to be M1. That's my rule. So there's FG1, and I guess this has a weight too, doesn't it? And it's a heavier weight, FG2. And then what do I got? I guess I've got a normal force pushing up on the table here. So I've got an FN, call it FN2 if you want, whatever. And then I've got a tension force pulling up this way. Okay, so F tension, and then I've got F tension. Now, the first thing to consider when we first look at this, notice how I've got a 6 kilogram mass is hanging and an 8 kilogram mass sitting on the table. So the first thought might be like, well, won't this just not move? Like, won't it go nowhere? Because isn't there a heavier mass sitting on the table and a lighter mass hanging? And this is where I think the unfolding thing kind of helps us figure out what's really going on here. Because when I look at this picture, it's not immediately obvious that the four FG1 and FG2 are not fighting each other. FG1 and FG2 are not in opposition. Since the pulley only goes at 90 degrees, this mass here, the hanging mass M1, wants to fall down. And since the rope here is pulling to the right, mass 2 wants to go to the right. So if I leave mass 2 where it is, and I take mass 1 and I just unfold mass 1, then my diagram kind of looks like this. I've got mass FG1 going this way. There's FG1. And then FG2 is going this way. It's still say downwards. I don't need to unfold the other half of the problem. So I've got a normal force up this way, and I can see that it makes sense that FG1 isn't fighting FG2 because what's balancing FG2 is the normal force. That's supporting the weight that's sitting on the table. So now I've got my tension inward this way and backwards that way. And I can see here that really what's happening is FG1 is winning, right? So FG1 is winning and there's no force backwards. So to find the acceleration, if the hanging mass, if FG1 is pulling and nothing's pulling back against it, the other thing you might say is, well, should we just get free fall, right? Like if there's no force opposing the mass 1 falling, then isn't our acceleration just 9.8 meters per second squared? Well, let's have a little look, see what we get, and then maybe we can make sense of it. So I've got, for the whole system, F net equals, my winner is FG1. And I'm not going to do the whole plus tension minus tension thing because we don't need to anymore. We've got that figured out. There is no loser. There is no losing force overall, so this is going to equal MA. But here's the important kicker, is that if I'm looking at the whole system, then this has to be the total mass here. And right away we can see that, no, the acceleration is not going to be free fall because the hanging weight that's pulling down has to accelerate not just itself, but also the mass sitting on the table. So the acceleration is going to equal FG1 divided by the total mass, which is M1G divided by M1 plus M2. So what do I have? I have 6 times 9.8 divided by 6 plus 8. Okay, and we can see that we get an acceleration of, it's like right around 4.2 meters per second squared. Okay, right? And that sort of makes sense. If the two masses were equal, I'd expect it to be about half a g. All right, so last I need to find the tension on the rope. Now for me, just looking at this picture, this system, this part of the system to me is going to be simpler to do. So let's just look at, we'll just look at M2. So I've got a net force equation. F net is going to equal tension force, which is going to equal M2A, and there's nothing opposing that. So I just sub in my values, and I have 8.0 times 4.2, which gives me an acceleration of right around 34 newtons. Okay. There's one more example here, which is what happens when we throw friction in the mix. And so I'm going to encourage you to try that one on your own, see how you do with that. A little bit trickier, but I feel like you can do it. Okay, and that is it for tension.